Hello, sir, here for the fourth lecture in the series on Hadamard matrices. So now it's supposed to be a bit more specialized, but we'll talk about bistochastic matrices. So what's the idea here? A matrix is called bistochastic if the sums on all the rows and all the columns are equal to the same number. And it's actually true that any complex Hadamard matrix can be put in bistochastic form. That's a particular case of something from very deep from symplectic geometry. It's not non-explicit, but well, the point is that when talking about bistochastic matrices, we actually talk about all the Hadamard matrices. They can be put in bistochastic form. So it's going to be a talk about all Hadamard matrices. Finally, not that specialized. So that was the idea. Now let's find this presentation. So here we go. Bistochastic Hadamard matrices, as I was telling you. So bistochastic means sum on all rows and all columns are equal to a common number, and we'll get to that in a minute. I mean, that's a deep result that any Hadamard matrix actually can be put in bistochastic form. Now, what's the motivation for doing all this? Well, let's just take the Fourier matrix F2. You see, I have here F2, and here what I do in order to put it in bistochastic form. This cannot be put in bistochastic form over the reals, right? Because over the reals, the equivalence relation, you always end up the same matrix, but the -1 at different positions. So it's not possible. But we can do it in complex one, multiply by I here. And then by -I here, I get this. And well, this looks better. I don't know. At least that's my opinion. I mean, this is more beautiful than this, right? It looks more balanced somehow. So this suggests really, even for real matrices, this is something very interesting. So they look better in complex bistochastic form. And well, the subject is quite new. I mean, underdeveloped, but the idea somehow this might lead to some advances on the Hadamard conjecture or circular Hadamard one, just by putting them in bistochastic form, complex. Maybe there it's better, among other motivations. So yeah, there are many interesting things here going on. So to begin with, what are some basic examples? So first of all, well, the complex Hadamard matrices are stable and they're permitting row and columns, the bistochastic ones. Also taking tensor products. So here's your computation here, just the sum it works. Now as basic examples, any circular matrix is bistochastic, right? This is clear. And it's the same row, which is circling like this. So the sums are the same, and on the columns you get the same thing, right? So in particular, we learned last time that the Fourier matrix can be put in a circular form. So that's of course bistochastic. We also vaguely talk, I think, about Fourier G that cannot be put in circular form, but can be put in bistochastic symmetric form. And also construction by Bachelin, I think I vaguely mentioned to you that these are circular, so they're also bistochastic. So yeah, I mean, interesting examples. Bachelin is also related to Fourier, so somehow things coming from Fourier tend to be bistochastic after some manipulations. We'll be back later to this. These are just some basic examples. Now, well, let's see a bit how the theory goes. So the first remark is that row stochastic is more or less equivalent to column stochastic. Bistochastic means both, okay? But under the assumption that the row sum is the correct one, meaning absolute value square root of n. So how to prove this? So assume first that we have H, there are several things here in this theorem. So assume that H is bistochastic with sums lambda, okay? So let's prove that lambda square in absolute value is n. So why this is true? Well, this is the trick here. So you take these scalar products, H1, the first row, with all the other rows. of course, it's only H1 scalar H1 matters, and this gives you n. The rest of the scalar products are 0. So this is n. And now if you expand all this, you'll get a sum over ij, you sum over j, and here you get lambda bar, and here you get lambda, so you get lambda square. Okay, that's the trick. So lambda satisfies this for a row stochastic, for a Bistochastic matrix. Now in the other sense, assuming that H is row stochastic, and the row sums have the good absolute value, which is square root of n, my claim is that the matrix is Bistochastic, because row stochastic with some lambda means H psi is lambda psi, psi being the whole one vector, right? Because multiplying by the whole one makes the sum of rows. So now you can use the adjoint and apply a bar here, you get your thing. Okay, so it's better to view this in matrix form, this Bistochastic condition. So one vector. Now another thing which is well known in the real case, and I don't know who was that, maybe Seberry or Mitrulia, I don't remember. It's about the excess that it satisfies this by Cauchy-Schwarz, and the equalities when H is Bistochastic. So if you look at this Cauchy-Schwarz estimates, which uses the fact that H is of norm square root of n, because the rescaled is unitary. So if you look at the equality, well, the vectors must be proportional. So this is more or less your Bistochastic condition. You use the previous result for getting it on both rows and columns. So we'll be back to the excess later. Now, what else can be said? Yeah, that big thing I was telling you, Ida Wolf, that any matrix can be put in Bistochastic form and unitary. So here, let me tell you a bit about this. It's quite recent, a few years ago. So the idea is to reformulate everything in terms of symplectic geometry things. So first you have the projective space, right? You take C and you remove 0, and it's the lines there. And inside this space you have the torus there, which is called Clifford torus. So it's a quotient of the usual torus. Inside that, it's a projective torus. They call it Clifford. And now the point is that, so you take a unitary matrix, right? Not Hadamard, it's more general. I mean, recall that Hadamards are rescaled unitary, so we'll just talk about unitaries in general. So this can be put in Bistochastic form, which means by multiplying rows and columns by numbers of modulus 1, which in matrix form reads U prime LUR is Bistochastic, L and R being both diagonal unitary. So these are the numbers which you multiply with. And then the standard torus, somehow when you move it by U, it's disjoint from itself. Well, this is pretty clear. I mean, you use this calculus with that whole one vector, you get it with psi. And also projective version of this, the Clifford torus, when you move it by U. Sorry, no, it's not disjoint, I'm saying. So the solution here precisely are this vector somehow, L and R, viewed as vectors are produced by this. So this is all elementary, it's by the Wolf. Now, the thing is that this thing here comes the point, is that, yeah, that thing here, in terms of symplectic geometry, is the following thing. So this Clifford torus is a Lagrangian submanifold, and the multiplication by U is a Hamiltonian isotopy. And the big result is symplectic geometry, so conjectures of Arnold, things like that. It's non-explicit, the proof, and non-trivial, is that this Clifford torus cannot be displaced from itself via Hamiltonian isotopy. I mean, you always have something in the intersection there. And now, according to this, so this is satisfied. So finally, your matrix can be put in Bistochastic form, but it's non-explicit. So as a consequence for us, this was for any unitary. Now we're interested in Hadamard. So of course, these are rescaled unitary, so they can be put in Bistochastic form non-explicitly. Now, well, this is quite difficult, so we'll be back in a second to it. So it's not clear. Maybe for Hadamard something can be done. I mean, explicit, that would be very, very interesting. So let's first get into some, yeah, let's see a bit what's going on with other things. So an interesting question is in the Watson case. I mean, the real Hadamard matrices, like the Fourier, cannot be put in Bistochastic form inside the reals, right? It's complex. But what about Watson in general? Let's see which matrices, when does it work and when not. So, well, the point is that you have this obstruction here. So you take the Watson class H and L, and if there are Bistochastic matrices inside, there are some equations to be satisfied for the integers. So this comes from the fact that, remember, the row sum of a Bistochastic matrix must be a number lambda satisfying of absolute value square root of n. Now, this number appears as the row sum, so it's a sum of roots of unity, right? With coefficients say 0, L minus 1. So there are n entries in the row, so this number satisfies this, and then your lambda is this. You see, so you get these two equations. Now, let's see what's going on when n is small. So for the real matrices, that's the well-known result. I don't remember what was that again, because it's very, I don't remember. Or maybe before. So n must be 4n squared if there are Bistochastic matrices there. But by the way, these guys in Hadamard are called regular, but we call them Bistochastic because that's the I don't know, an analyst, so we call them Bistochastic there. So the result is that, yeah, in order for regular matrices, Hadamard matrices to exist, here we call them Bistochastic and must be a square. Now when L is 3, you get this kind of thing. Why? Yeah, that was the equation, okay? So you have to sum roots of unity of order 3. And the absolute value squared is given by this tricky formula. A simple exercise. So it's half of a sum of 3 squares. So you see you need with sum 0. These guys sum up to 0. So these 3 guys, integers summing up to 0, whose squares sum up to 2n, which is not, can happen or not. Well, this is just the beginning. I mean, you can get beyond this, of course. For L is 4, also n must be a sum of 2 squares, right? Because a plus ab is this. So there are many obstructions here, or these are quite similar to what happens for circulant matrices. I mean, these obstructions apply also to the circulant case, worked by Turin and many others. Now, let's discuss one other problem, which is putting matrices in Bistochastic form explicitly. So we already know that Fourier can be put in Bistochastic form, right? Explicitly, that was that because it can be put in this circular form. That's the story with the cyclic roots we discussed last time. It's very explicit. So now what about these deformations? And the point here is quite interesting. You can do it for Fn tensor Fn. That's this is a deformation of n tensor Fn. So you can modify it in this way. I mean, this matrix with the prime here, there's the formula, and it's like Bistochastic. It's almost. I mean, the row sum have the same absolute value, so it's just enough to multiply them by numbers on the circle and get a Bistochastic matrix. So this works definitely, and which is not really obvious. I mean, I found this thing. I had to work a bit for it, finding it. But the problem now is that if you try Fn tensor Fm, we don't know. So let's first take a look at this. So the simplest example is, of course, F2 tensor F2. So if you plug in all these things, you get this matrix here, which is, you see the row sums are 2, minus 2, 2, 2. So it's just enough to flip this by minus 1 to get your Bistochastic matrix. So it's explicit, and it works for any Fn tensor Fn. Now the question is that, yeah, it would be very interesting to do it for Fn tensor Fm and many other matrices to see if that's an open problem, okay? Any Hadamard matrix can be put in Bistochastic form non-explicitly by this Tidal-Wolff thing based on symplectic geometry non-explicit, but in the case of Hadamard matrices, so this was for arbitrary unitary Seidel-Wolf. Can you do this explicitly for Hadamards? And it's not clear, so that would be a candidate here. And also, especially all these real matrices like Pelly, Williamson, other, because assuming, for instance, that you can put Walsh, of course, can be put in Bistochastic form. We did it in the beginning, right? F2, you know how to do it, and then it transfers itself, you're done. But Pelly and Williamson, these are keys in computations, because if you can ever put them explicitly in Bistochastic form, it means that somehow the whole real Hadamard matrix theory, including all the difficult problems there, Hadamard conjecture, circulant one, can be reformulated in complex Bistochastic form. Maybe they get simpler, I don't know. Just an idea. So difficult algebraic questions here, definitely work to be done here. Now, let's go to another thing, one more thing to finish with. So that's an attempt. It's going to be 8 slides in a row, so a lot of, it's an attempt to understanding the excess, the distribution of the excess as a probability measure over the equivalence class of H. So let's not start in a real case because it's quite interesting. So we'll take real Hadamard matrices and the real equivalence class. And the distribution of the excess is called the glow. So you can define it like this. Well, if you like really explicit formulas, that's it. It's the same thing. So it's the glow. I mean, it's like a city having a glow. So imagine a square city with, you see, that's my city over here, with street lights at crossroads, and you switch them on when evening comes. Our positions where your Hadamard matrix is 1. And you switch it on and off randomly with the switches on each row and each column. So the glow of the city is exactly this. Yeah, that's why we call it the glow. All this is, of course, the game, Bernoulli game for Hadamard matrices, right? That's exactly the game. So they actually had a wooden game there at AT&T. I don't know when was that, 60s maybe. They're playing with it. Quite fun. So that's why we call it the glow. And we have 2 results. So first is something algebraic, which is quite interesting. So if you, well, the glow, of course, is supported to do some simple things, and it's supported not by the integers, but actually by the multiples of 4. So simple arguments there, modulo 4. And then you divide it into 2 parts, the odd and even part. I mean, odd is 8z, of course, and even is, no, even is 8z. Odd is 8z plus 4. And the thing is that, so mu even mu odd are the thing, but rescaled as to have mass 1. Now there's an interesting thing happening. So depending on n, whether it's 0 or 4 mod 8, you see the measure splits between numerator nodes, 3/4, 1/4, or 1/4, 3/4. That's quite fun. And the proof is not trivial. You have to use this, well, you have to take this picture and write somehow your probability thing. So maybe, yeah, something like this. So you get some convolutions of Bernoulli laws, a big sum where all switching indices of some convolved Bernoulli. So it's all about Bernoulli, the combinatorics you get to this. And I think algebraically, this is the only thing that can be said. So I did a lot of computer simulations and nothing beyond this. So that's the only property of the glow algebraic. Analytic now, that's quite interesting. The glow becomes Gaussian, then it goes to infinity. I mean, it can only become Gaussian, right? What else can it be? And the proof is via the moment method. So you see the excess is this. We're trying to compute the load of the excess. So I raise this to the power r, get some integrals here over z to n. And well, this the integrals over z to n are correspond somehow to partitions with even blocks. So we get something like this. Then we combinatorics, like Möbius formula, something like that. And you get to 2p double factorial at order 0 and then other terms. And 2p factorial means Gaussian. These are the moments of the Gaussian law. So this was the real case, so quite fun. So definitely you have the Berlekamp game, something algebraic, which is quite nice, and then Gaussian. In the complex case, let's go to the complex case, which is more interesting now. So we define the glow in the same way, but now the lights, instead of being on and off, they are allowed to take values in T, right? So, or square. I remember we had the city, square city, and we have switches here, 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 here. Now the switches are continuous, right? Because we can multiply by numbers in T. So, but once again, yeah, the definition is this. I mean, it's the law of the excess over the Hadamard equivalence class, but which is now complex. So in the formula, yeah, that's the formula. It's the same thing. So some basic property. First of all, it's invariant under rotation, of course. So in particular, that's a complex measure. Being invariant under rotation, it's just primarily a positive measure, which is convolved by the epsilon is the uniform measure on the unit circle. Now, well, this can be defined, of course, for a complex matrix. So yeah, let's do things slowly. So when it's a multiple of a unitary, which is the case for Hadamards, the support is smaller than n square root of n. That's of course because the excess is smaller than n square root of n. We talked about that when doing the basic theory of the excess. And finally, well, also it's unitary. Actually, this guy here, this bound is attained for a support. It's optimal. And this is the Wolf result. I mean, remember the excess attains its maximum when the matrix can be put in Bistochastic form. But when it's unitary or scale unitary, this does happen by the rule for the symplectic geometry things. So the excess attains its maximum. So this theoretical maximum for the disk containing the support of the glow is the optimal one. So you see, it's all these little full things finally are about the support of the glow. That's good motivation for studying it. What can be said? Well, once again, what else can you expect? As in the real case, it becomes Gaussian, but this time complex Gaussian. But so this is a bit better than in the real case. You have two terms, term order 0. You see there is a 1 over p factorial hidden here, okay, in the beginning. So have order 0 term, and I also have something at order 1, fluctuations. So very nice. Proof, once again, moments combinatorics, actually quite, I don't know, 5 pages of combinatorics. So that's a bit tough, a lot of partitions and everything. And now the point is that for Fourier matrices, you can go up to order 0, 1, 2, 3, 3, and actually even order 4. And it's very interesting because the glow, no matter your Fourier matrix, of course it depends on your size. That's the big N parameter. So you see all these numbers here, they don't depend on n. I mean, it's Gaussian, and the fluctuations of order 1, 2, 3, 4 don't recognize the group. It's quite strange. But the next term, if you look at it, there is this E here, which is the number of even numbers among N1 and K, N1 and K being the indices of the cyclic groups there appearing in the decomposition of G. So yeah, a bit strange all this. And so finally the glow, yeah, I can read finally the group, but you have to go up to order 5. So it's quite a strange invariance. I think a very good question is that of computing the glow of the Walsh matrices, but the complex glow. For yeah, for some complicated reasons, I think that's the good problem. Okay, so I guess this was it. So very interesting questions. So we basically have here the complex Hadamard matrices can be always put in Bistochastic form, and that's extremely, extremely interesting potentially in the real case for the real matrices. But there is the rule thing, I mean, these symplectic geometry things that are non-explicit. So there's a lot of work to be done in order to do things explicitly. This is not done yet. And also there is an analytic approach to this thing with this Berlekamp game and the glow once again, a lot of work to be done there. So that was it. And next two lectures, that's going to be next one, almost all of my matrices. So some work with Nikita Ziskovsky. It's more personal. It's going to be not really Hadamard, some generalization. And the last lecture will be about quantum group. So see you soon and for the next lecture.